Good day, everyone. We are the Group Innovate, and today we are presenting our project entitled Students' Performance Prediction System Machine Learning for Pass/Fail Classification. This project focuses on applying machine learning techniques to predict student academic outcomes and identify students who may be at risk at an early stage. Through this system, we aim to support educators in making earlier and better informed decisions. Now let's move forward. Now let's move on to the project overview. The Student Performance Prediction System is a machine learning web application developed to identify students who may struggle academically early in the term. The main goal of the project is to predict whether a student will pass or fail without relying on prior grade history such as G1 and G2. To achieve this, we conducted a comparative analysis using three machine learning algorithms. First one is the K nearest neighbors or KNN. Second one is the support vector machine or SVM. And the last one is artificial neural network or ANN. This allows us to determine which model performs most effectively. Now let's move forward to this code. Traditional approaches rely on midterm grades, which arrive only after the damage is done. This project enables intervention before exams exist. Traditional approaches in identifying struggling students often rely on midterm or already existing grades. The problem with this approach is that by the time these grades become available, students may already be experiencing, of course, academic difficulties. Our, pro- our project addressed this issue by making predictions before exams even exist. This allows schools and instructors to intervene earlier and provide support before a student falls behind. Now let's move on to our team composition or our project team. Our project was completed through collaboration among three members with assigned responsibilities. Christian Gonzaga, which is myself, served as the backend developer and handled the Flash application development, machine learning pipeline, construction, and model training. Andres Estrada worked as the front-end developer and focused on designing the user interface and interactive dashboard. Lastly, Kevin Galvez served as the data analyst and handled dataset collection, pre-processing, and performance evaluation. Through teamwork, we combined our skills to effectively and successfully complete the system. Now let's move on to our dataset. So our dataset source is the UCI machine learning repository, and our student count is 395 students, along with the feature set of 30 predictors, which is demographics, habit, factors, and many more. Now, the excluded features is G1 period 1 and G2 period 2 and G3 final grade. Now, this was done in order to prevent data leakage, in order to allow the training models to not see biased data. For our target variable, we have the binary result of pass or fail. The dataset became the foundation of our study because it provided the necessary information for training and testing our machine learning models. Using this data, the system was able to learn patterns and make predictions regarding student performance. Now that's all for my part. Let's move on to Andres Simon Estrada for the continuation.
Now for the data processing pipeline, before training any model, the data goes through a 7-step pipeline. First is we have to detect the file separators, handle missing values using median and mode imputation, and then encode categorical columns with label encoders and apply standard scalar for normalization. We derive the pass or fail label from G3, strictly excluding, like Christian said, the G1 and G2 to prevent data leakage. And finally, split the data 80-20 with stratification to preserve class balance. Now for early intervention, so this slide explains a critical design decision on why we exclude G1 and G2. Including them would make the model dependent on grade history that simply doesn't exist at the start of the term. This defeats the whole purpose. By removing them, the model learns entirely from a demographic and behavioral signals, meaning it can generate fair prediction before the first exam is even taken. Now for the classification algorithm, we implemented three algorithms, the KNN, CVN, and yes, ANN. The first is the KNN, the key nearest neighbors, a lazy instant-based learner that classifies a students by majority vote among its five most similar neighbors in feature space. Second is the support vector machine with RBF kernel, which finds the maximum margin hyperlink in high-dimensional space, allowing it to capture complex and non-linear decision boundaries that simpler method would miss. Then next for the next supporter is Kevin Galvez.
Moving on to our third and most complex algorithm, we implemented deep learning using a multi-layer perceptron or ANN. Our network utilizes a fully connected feed-forward architecture with two hidden layers, the first containing 64 neurons and the second containing 32. To optimize this network, we used a few specific configurations. We used a ReLU activation function for high efficiency, the ADAM optimizer for adaptive learning during training, and finally, a sigmoid output layer to give us clear probability outputs for our binary pass or fail classification. Now, moving on, let's look at the overall performance comparison across all three models. We evaluated these results on a held out 20% stratified test set to ensure our findings were unbiased. Looking at the table, you'll see we focused heavily on the F1 score and recall. The KNN model gave us a balanced baseline with a 77.97% F1 score. Our ANN actually achieved the highest precision at 72.41%, meaning when it predicts a pass, it is highly accurate. However, our clear winner is the Support Victor Machine or SVM, marked here as our best model. It achieved the highest overall F1 score at 79.34%, driven by an exceptional recall of 90.57%. Moving on, based on these findings, we have three key recommendations for deploying this system. Number one is deploy the SBM. Because it has a superior recall of 90.57%, it ensures that the fewer or fewest at-risk students are missed during the early screening process. If the goal is to intervene and help failing students, we want a model that casts the widest safety net. Next is the local training. We recommend that institutions retrain the model using their own specific CSV data. Every school's demographic is different, and local data will improve calibration and F1 scores for that specific student population. Third and the last is ethical use. It is crucial that these predictions are used to support human advisors, not to automate gatekeeping. Human review and strict privacy compliance are absolutely mandatory. We are building a tool to help students, not judge them. Next slide, please. And by implementing this system, counselors can step in weeks before midterm grades even exist, bridging the academic success gap before it's too late. I will now pass on to the next reporter, which is Christian Gonzaga, for the live demo of our prototype.
Now, this is our system. This is the student's performance prediction system or the neural decision engine. Now, this is our simple dashboard. First, let's move on to our workflow. So how exactly does our system work? So it has 8 overall steps. First is the problem identification. It predict pass versus fail from student attributes. Second is the data collection, which we import the file or the data set. Third is the data preprocessing, which handles missing values, encoding, scaling, split, and many more. The fourth one is feature selection, which we drop G1, G2, G3 from predictors to, of course, avoid data leakage. The fifth one is model training, fit for KNN, SVM, and ANN. And the sixth one is model testing, evaluate on 20% held out test set. And the seven is performance evaluation. That is, we include the accuracy, the precision, the recall, the F1, and the confusion matrix. The eighth one and or the last step is prediction output, where we score the new students on our predict page. Now let's go back to our dashboard. So for the first step, we will of course choose the file or the dataset in which we used to train. So we of course choose file and select our dataset. And as we can see here, it says active file student data.csv. Uh, After, of course, it will then show the information or the basic preview information of our data. That is first rows, there is 395 total rows in our data set. For the columns, there are 33 columns, and for the missing values, there is 0. However, just to ensure that, we applied, of course, the pre-processing and features. First is to handle missing values, median for numeric, mode for categorical. We created target result, pass 1 if G3 is greater than or equal to 10, or else fail. label and code each categorical column. Feature selection, of course, what we mentioned before, we excluded G1, G2, and GT from predictors, and we applied standard scalar to all features, and we split data 80% training and 20% testing, stratified, and the random state of equals to 42. Here is the numeric summary of our table along with all its columns and some of the rows. I will just scroll through it for the preview. And for the dataset preview as well here for the first 20 rows. So here is the first 20 rows. And of course, once we finish verifying everything, we simply just click train KNN, SVM, and ANN. After we click this, we wait for a few minutes and it will mention here train KNN, SVM, and ANN on 316 samples, test 79. And it will, of course, recommend the best training model, which is SVM. So here is the system insights and recommendation, which serves as our summary. So system recommendation, use SVM. It has the best F1 score, which is 0.7934, and the highest accuracy of 0.6835. The pass rate in data is 67.1%. Here is our conclusions. So among KNN, SVM, and ANN, SVM achieved the highest F1 score on the held out test of 79 samples. For the accuracy ranking, the first rank is the SVM, the next is the KNN, and the last is the ANN. And of course, F1 score spread between best and worst model is 0.0366. Models perform similarly, any may suffice for prototyping. Approximately 67.1 of students in the dataset pass G3 is greater than or equal to 10. Class imbalance may affect precision/recall, and of course, interpret metrics accordingly. The model flagged 20 students as pass who actually failed false positives. Precision could be improved for stricter screening. And we have correctly identified 23.1% of failed cases and 90.6% of pass cases. So for the recommendations, we are to deploy SVM for production style prediction using the predict page. Use the predict page, which we'll see later on, to score new students early without G1, G2, G3, and plan support for those predicted to fail. Retrain after uploading a new dataset so metrics and recommendations reflect your organization's data. So here is our chart. So model performance comparison. Here's our test set. As we can see, the blue one is the KNN, the purple one is the SVM, and the orange one is the ANN. For the overview, we can clearly see that for most cases, SVM is on top. It is only in precision in which the ANN exceeds the two other models. So here is the metrics for comparison. We have, of course, the rank 1, the SVM, the rank 2, the KNN, and the rank 3, which is the ANN. For the accuracy, of course, we have the highest for the SVM of 0.6835. Next one is 0.6709. And the third one is 6.582. For the precision, SVM has 0.7059, KNN has 70.7077, and the third one is 0.7241. For the recall, SVM has 0.9057, the second one is 0.8679, the third one is 0.7925. And for our F1, of course, rank 1 is SVM of 0.7934, the second one is 0.7797, and the third one, ANN, is 0.7568. So here is our uh, actual predictions, and actual fails and actual pass. For the KNN, actual fail 7, and the actual pass is also 7. For this instance, for the KNN, is instance-based learner, K is equals to 5. Strong when local neighbors are similar, sensitive to feature scaling, which is of course already applied in our system. For our SVM, which is of course our recommended one, RBF kernel SVC with probability estimates, often strong on medium-sized tabular data with nonlinear boundaries. So for our ANN, we have the feed-forward network, which is 64 to 32 ReLU units. It captures nonlinear interactions and may need more data or tuning if, of course, underperforming. So we can see the predicted fails for the students, and of course the actual number of failures for the students, and the predicted pass, and of course the actual number of actual pass in our students. Now we also have here a dashboard to predict a student in which we can change their values and of course determine if ever they will pass or they will fail. So here we can, of course, change the travel time to higher values, the study time to, of course, higher values, failures to higher values, and for go out, we can, of course, set lower values, and we can choose which model we have to use. So in this case, let's choose the recommended model of SBM, and let's predict pass slash fail. So here, the model of SBM is it actually dictated pass. So we can also compare all three models, which states here KNN 80%, SBM 68.5, and ANN is 72.5. So here in this specific data, actually in the confidence level, we can see that KNN has the highest number. So if we go back to this and click KNN, then we can predict pass slash fail, and we can see that it has 80%. So that is all for our system demonstration. That is student performance prediction system, and that is all for Group Innovate. Thanks so much for listening, and God bless.